Hi, welcome to videos on analog filters. So in this video we'll see the first order lag network. This is the general transfer function of a first order system. So showing the position of a pole which is at omega naught, and of course there is a zero located at a naught by a1. So this is the general transfer function. So let us see the same transfer function slightly rearranged in this way. So now we are trying to see there is a pole located at omega naught, and there is a 0 at a naught by a1. Of course this is the constant term. So what we are assuming here is that let this a naught by a1, which represents the position of 0, let that be far greater than omega naught, which is the position of a pole. So that's what is depicted here in this pole 0 plot. So here we have the position of a pole which is at omega naught from the imaginary axis. Of course the 0 is located at a naught by a1, which is assumed to be larger in magnitude compared to omega naught. So this is a transfer function of a lag network, which means that you're going to have pole first followed by a 0. So let us see how does the Bode plot of the same look like. So this is the Bode plot of the lag network. So if you can see here, initially there is no 0 or a pole, so that's why the slope is 0 dB per decade. So after a frequency omega naught, so there is a pole comes into existence. That's why the slope decreases with a slope of minus 20 dB per decade. And you can see when it is keep reducing, there is a 0 coming across at a naught by a1. So afterwards, after this frequency of a naught by a1, the slope again becomes 0 dB per decade. So meaning at omega naught we have a pole, and at a naught by a1 there is a 0. So initially slope is 0 dB per decade, then it becomes minus 20 dB per decade because of the pole, and then it again becomes 0 dB per decade because of a 0. So here in this example we are assuming omega naught to be 1 kiloradian per second, whereas a naught by a1 happens to be 10 kiloradian per second. This is the assumption what we are assuming. This is the phase of that lag network. So if you see this is the expression, the terms that are contributing to phase are this omega naught and a naught by a1. Since this is the position of, this is the representation of a pole, the phase contributed by pole is minus tan inverse of omega by omega naught, whereas the phase contributed by a 0 is omega by a naught by a1. The value of omega naught, which in this case happens to be the pole frequency, if it is 1 kiloradian per second, and omega of z, that is the 0 frequency, if it is 10 kiloradian per second. So as we know that there is a change in the phase happening, so maximum phase will occur at the square root of omega p into omega z. We'll see what is the significance of that here. Of course we assume that omega p to be 1 kiloradian per second, which corresponds to 1.59 kilohertz, and corresponding 0 frequency in hertz happens to be 15.9 kilohertz. The frequency at which maximum phase will occur is at 5.02 kilohertz, and this is how the phases keep changing. If you can see, if you consider the pole at 1.59 kilohertz and 0 at 15.9 kilohertz, the phase will be maximum at 5.02 kilohertz. That phase happens to be minus 54 degree. So if you substitute in the previous expression of phase, if the omega is equal to 0, then you get phase as 0 degree, and even if you substitute omega is equal to infinity, you get 0 degree. So we will get maximum phase at 5.02 kilohertz in terms of hertz, and otherwise it will be 3.16 kiloradian per second. We'll see both these verifications in both 20 sim as well as. So this is the 20 sim simulator simulation what we'll be seeing. If you can see here, you can see this is the position of the pole, so which is located with a time constant of 0.001 second, whereas the frequency of this happens to be 1 kilohertz, whereas 1 kiloradian per second. the position of 0 is having a time constant of 0.0001, which corresponds to a frequency of 100 kiloradian per second. So we will see the implementation of this in 20sim. So let us see how we can edit this. So this is, I think we already have, there is a pole located at point 0.001. If you can see, there is a 0 located at point 0001. So let us see the pole 0 plot. So first pole should come and then the 0. So this is the pole 0 plot what we are looking at. Yeah, exactly. You can see there is a pole at minus 1000, which is the distance from imagined axis is 1000, whereas the 0 is located at minus 10,000. So this is the location. This is the pole 0 plot of a lag network. Simultaneously, let us see the Bode plot of the same lag network. So this is a Bode plot. As we thought, you can see initially there is no slope, and the slope is becoming negative. You can see the magnitude is keep coming down. So at 1000 radian per second, this will be 3 dB exactly. In asymptotic plot, we're going to get till here it is constant, and then it goes with a slope of minus 20 per decade. That is the asymptotic one, but this is the actual plot. So there is a difference of minus 3 dB from the actual and the asymptotic, which can be clearly seen here. This corresponds to minus 3 dB at 1000 radian per second, which is the location of a pole. And you can see there is a 0 available here. So this is the location of 0, which is at 10,000 radian per second. It's again at minus 3 dB from that 10,000 point. You might have seen in the previous calculation that the phase happens to be minus 54 degrees at 3.16 kilohertz. Let us observe the same thing here. So let me just move this cursor so that what is the maximum phase you're going to get. If you can observe here, this is the y value, that is the phase, this is the frequency. So we know that at 3.16 kilohertz the phase was minus 54 degrees, which is almost there here. You can see it's almost 3.2 kilo radian per second. So let me slightly go to left side, which happens to be 3.16 kilo radian per second, which is exactly here. You can see 3141, and this is minus 54.9 is the angle. So that's what we have seen here. You can see here is the phase what we are looking at. You can see this is minus 54 degree at a frequency of 3.16 kilo radian, which is exactly seen over here. So this is that particular frequency, and of course as the frequency is lower and lower, the phase is almost equal to 0 degrees. So if you start from a very low frequency, so this will be almost 0 degree. So as the frequency increases, it again goes to almost 0 here. So this is how the phase of the plot will change, and this is the magnitude plot. So magnitude initially 0 dB per decade slope, then reduces and then becomes almost again constant, that is at 0 dB per decade. So this is the demonstration of a phase lag network in 20sim. We'll see the demonstration of same lag network in the LTspice also. Before that, we'll see how does the circuit of this RC network will look like. So let me go to this. Let us see the circuit. So this is the lag network circuit diagram. If you can carefully observe, this R1 and C is actually a low pass filter. This is an extra component that is coming in case of a lag network. If you consider only R1 and C, so this is a low pass filter having a pole at 1 over 2 pi R1 into C, and there was no 0 located. 0 is actually located at infinity. If you put a resistor R2 in series with this capacitor, the 0 which is at infinity will come to a finite value. So let us see the transfer function of this. So this is a transfer function. If you can see here, on the numerator you have 1 plus S R2C. So this is a time constant of S0. 0 is now located with the time constant of R2 into C. Whereas the pole is now located at a point which is having a time constant R1 plus R2 into C. So this R1 plus R2 into C happens to be the time constant, whereas the frequency of that happens to be frequency of 0 happens to be 1 over 2 pi R2 into C, whereas for pole it is 1 over 2 pi R1 plus R2 into C. So let us see, if I consider the value of R1 to be 1K and R2 to be 10 kilo ohm, and if this value of C is 0.1 microfarad, if you can carefully observe here, this CR2 will represent, will actually demonstrate, or will actually decide what is the pole, zero position. Since this is 100 ohm and this is 0.1, the pole is at, the zero is located at 15.9 kilohertz, whereas the pole is almost very close to located to 1.59 kilohertz. This is not exactly, this is very close to 1.59 kilohertz. If you can see, this is the expression for zero position and the pole position, which is exactly represented in this S-plane pole zero plot. So let us see the demonstration of the same circuit in LTspice. So let us take the LTspice circuit. Okay, this is a circuit what we are looking at as a lag network. So this is R2 and C1, which represent the zero position, and R1 plus R2 into C1 will represent the pole position. So let us do the frequency response, for which I am doing .ac decade. Let me run this. In this case also we will go to get the phase of minus 54 degrees at 5.02 kilohertz. It is not in terms of radian per second. So let us see what is the magnitude. You can see here it is 0 dB, it just goes down here. So the slope reduces to minus 20 dB per decade, and then it becomes again constant. So this is exactly similar to the Bode plot what we have seen over here. So let me just show both of them one to one. You can see they are exactly. So let me just slightly adjust. Okay, these two are exactly the same. Now this is the 20 sim frequency response. This is the LTspice frequency response. If you can see in the frequency response of LTspice, the slope is initially 0, which is same here, and then slope reduces with minus 20 by decade. You can see it's happening same, and it again becomes constant, and you can see the same thing is becoming constant, and you can see this light line which happens to be the phase of it. So here you can see the phase is separated by a different plot. Only difference is that here this is in radian per second, whereas this is in hertz. So here we saw in the previous case the phase is minus 54 degrees at 3.16 kilo radian per second. So here this is minus close to minus 54 degree at a frequency of 5.01 kilohertz. So we'll just see the same thing over here. So let me just move that so that I can find out what is the frequency. You can see the frequency is almost 4.10 kilohertz. You can see the phase is almost minus 56 degree. So we are supposed to get it at 5 point. Okay, let me slightly move this so that I'll go to the minimum position. You can see you're there almost at 4.9. The phase is almost 56 degrees. Likewise, certainly verify the working of a lag network both in circuit simulator as well as the 20 sim control simulator. If you change the value of R2, only the of course if you change the value of R2, both the pole frequency as well as the zero frequency will change. If you change the value of R1, only the pole frequency will change. We just see that variation. If I change this to 10K, you can see if I change this to 10K, the zero remains constant, meaning this position remains constant. Only thing is that this will go down, this will go back. So let me run here now. So you can see this will be same, which is the position of 0. The pole will be further reduced. You can see it just goes back. Can you see it just went here? So it's almost 159 hertz instead of at 1.59 kilohertz. And of course you have a phase of slightly increased phase. So phase will naturally depend on the position of poles and zeros, because the phase, the center frequency depends on square root of fp and fz. And of course the magnitude of the phase will also differ. You can see magnitude of the phase is almost going up to minus 80 degree. In the previous case it was minus 54 degrees. So this way we can able to achieve whatever required phase you want at whatever frequency using this phase lag network. So always the phase is negative with respect to input signal. We'll see in the next slide, next video,